Now let's see the classification of complexes. Here you can see the major types of complexes. The first one is metal complexes, second one is organic molecular complexes, and the third one is inclusion complexes. Inorganic type complexes, chelates, olefin types, aromatic types. These are coming under metal complexes. Organic and caffeine complexes, polymer types, picric acid types, quinhydron types. These four are coming under organic molecular complexes. Channel types, layer types, chelates, monomolecular types. These are coming under inclusion complexes. So these are the major types of complexes. Now let's discuss about metal complexes. What are metal complexes? In this type of complex, metal ion constitute the central atom. It is known as substrate. Okay, in metal type complexes, there is a central atom which is a metal ion. So it is known as substrate, or it is called as substrate. This substrate interact with a base which is called as ligand. This ligand is an electron pair donor. Now we are talking about metal complexes. In this metal complexes, metal ion constitute the central atom. This central atom is called as substrate. So this substrate interact with a base, and this base is known as, or this base is called as ligand. This ligand is an electron pair donor. As I previously said, the central metal ion or the substrate which is interact with a ligand or a base. This type of interaction leads to the formation of coordination bonds between the species. Okay, here you can see a central metal ion. This is our substrate. Around the substrate there are ligands, and the lone pair of ligands, that here you can see the lone pair of ligands, and these electrons are donated to the central metal ion. Like this, coordination bond is formed between the species, and our metal ion complex is formed like this. Inorganic complexes are the first type of metal ion complex. Okay, now move on to inorganic complexes. Inorganic complexes are a type of metal complex. Here you can see an example for inorganic complex. Here cobalt is the central atom. This is our substrate. And chloride ion and ammonia, you can see here, these are ligands. So this is coordination sphere. The first one is known as coordination sphere, and this one is known as ionization sphere. So this is an example for inorganic complex or a metal complex. Cobalt is the central atom which is known as substrate. Chloride ion and NH3 ammonia, these are ligands. Ligands are electron pair donors. And this one is coordinated sphere or coordination sphere, and the second one is ionization sphere. In solution, this compound ionizes and form components like this. This is coordination sphere. Okay, here you can see chloride ion. This chloride ion, which is present in our coordinated sphere, cannot be precipitated by silver nitrate. Okay, the chloride ion which is present in a coordinated sphere cannot be precipitated by silver nitrate. Chloride ion and ammonia, these are present in our coordinated sphere. These are known as ligands. So, you know, ligands always donate electrons to the central atom. As I previously said, the ligands which donate electrons to the central atom because of this coordinated bonds formed between the species, and like that our complex will be formed. Now let's see what is the coordination number of a central atom. You know what is coordination number? Coordination number is the maximum number of atoms or groups that can combine with the central atom in the coordinated sphere. Okay, have you remembered that coordinated sphere? So this is our coordinated sphere. Okay, this one is our coordinated sphere. Here cobalt is the central atom and chloride ion and ammonia are the ligands. Okay, so what is coordination number? It is the maximum number of atoms or groups that can combine with the central atom in the coordinated sphere. So here you can see ammonia 5 and chloride ion. So 5 plus 1, 6. So 6 is the coordination number of cobalt. Okay, here 6 is the coordination number of cobalt, and this coordination number is usually an even number. Okay, coordination number means it is the maximum number of atoms or groups that can combine with the central atom in the coordinated sphere. Now move on to another type of metal complex, that is chelates. Chelates are a group of metal ion complex. Chelates are a type of metal ion complex. In chelates, ligand provide 2 or more donor groups to combine with a metal ion. But in the case of inorganic metal complexes, the ligand provide only one site for binding with a metal. Okay. Depending upon the number of donor groups available for complexation, ligands are of different type. If 2 donor groups available for complexation, it is known as bidentate. 3 groups available, then it is known as tridentate. More number of groups are available, then it is called as polydentate. EDTA is an example for chelate. EDTA means ethylene diamine tetraacetic acid. Here you can see the structure of ethylene diamine tetraacetic acid. This is the 3-dimensional structure of EDTA complex with a metal ion. Here you can see the central metal ion, and it has 6 points of attachment. Okay, EDTA complex with a metal ion, and here you can see 6 points of attachment to the central metal ion. So it is known as hexadentate. This is hexadentate chelate. Diverse types of bonds are involved in EDTA, like ionic bond, primary covalent or coordinated bonds are seen in EDTA complex with metal ion case. Such types of bonds can easily seen in calcium EDTA chelate complex. So this is 3-dimensional structure of EDTA complex with a metal ion. Here you can see 6 points of attachment to the metal ion. In chelates, ligands provide 2 or more donor groups to combine with the metal ion. Here the dashed line that indicate bonds from the metal ion to the coordinated groups of the ligand. Okay, this dashed line indicates bonds from the metal ion to the coordinated groups of ligand. This type of complex may produce a precipitate or a stable water-soluble compound. If the ligand forms a stable water-soluble metal chelate, it is said to be sequestering agent. So, what is sequestering agent? If the ligand which forms a stable water-soluble metal chelate, then it is known as sequestering agent. Sequestering is the process in which the property of metal is suppressed without removing it from the solution. So sequestering is a process. In that process, the property of the metal ion, the property of the central metal ion is suppressed without removing it from the solution. This process is known as sequestering, and the agent used to suppress the metal ion without removing it is known as sequestering agent. Citric acid, tartarates, EDTA. These are sequestering agents. Chlorophyll and hemoglobin are naturally occurring chelates. Now let's see what are the important applications of chelates in pharmacy. It is used to increase the stability of a formulation. Purification purpose we are using this chelates. For analysis of drugs, and this chelates act as an anticoagulant. So these are some of the important applications of chelates in pharmacy. Increase stability. How chelates increase stability? It prevents oxidative degradation of ascorbic acid in fruit juices and drug preparations. Fruit juices and drug preparations may contain metal ions like iron, copper, etc. These metal ions that can accelerate the degradation of ascorbic acid. These metal ions may accelerate the degradation of ascorbic acid in fruit juices or drug preparations. While adding EDTA to this fruit preparations, this EDTA chelate with this metal ion. So the action of this metal ion is suppressed by this EDTA metal complex. Like this, we can prevent the oxidative degradation. While adding EDTA to fruit juice or drug preparations, this EDTA chelate with the metal ion. So the action of this metal ion is suppressed there. Like this, we can prevent the oxidative degradation of ascorbic acid. This is one of the important application of chelate. The next one is purification of hard water. Ethylene diamine tetraacetic acid is used to remove calcium from hard water. Like this, we can purify hard water. It is also used for the analysis of drugs in the assay of procainamide in injectable solutions. And this is based on 1:1 chelate formation with cupric ion at a pH 4 to 4.5. This assay is based on 1:1 chelate formation with cupric ion, and the assay is carried out at pH 4 to 4.5. Here the formed chelate is a colored complex. So we can estimate it by colorimetrically. So this is another one important application of chelate. Some of the chelates act as anticoagulant. For example, citrates, oxalates, EDTA. These are in vitro anticoagulants for blood. These ligands bind the calcium. Okay, so these are in vitro anticoagulants for blood, and these ligands bind the calcium, so it interfere with the thrombin formation. So calcium is not available for the clotting process. So clotting will not be occur. So these are the important applications of chelates in pharmacy.